Hello, everyone. Welcome to part two of chapter two. We had just ended off with the periodic table, and I did, as I promised, I updated this to include our state's element, and I had to do that. Tennessean is officially on this one, so there we go. So what we're going to do is discuss this in a way that hopefully we understand and helps us understand the chemical bonding. I will say that I found a little bit of a typo in the notes and fixed it where it said there is one type of weak bond that you need to know. And this, of course, should be not a weak bond, but a WEAK bond. That was a typo that I did not catch. So I'm going to go ahead and fix it now that I see it. See, I never see the typos until when I'm actually teaching it, and then you see them because you're looking at it in a whole different way. Now, what I want to talk about, guys, is that covalent bonds, ionic bonds, these will be types of chemical bonds, types of atomic bonds. Chemical bonds are associations between matter, between atoms and molecules. They happen because the valence shells may not be fulfilled. We'll talk about that, especially with a covalent bond. Ionic bonds, we'll talk about them. We'll talk about the hydrogen bond and the van der Waals interactions, which are very weak interactions, and discuss them. Now, as we start with covalent bonds, what I want to discuss with a covalent bond is this. Okay, is what is it and how does it form? Now, to do that, I am going to use my hover cam here and discuss that. And what I always like to do is make sure this is, in fact, inverted here. And okay, so what I want to do is discuss those bonds, and we will here. Come on, autofocus there for me. There we go. All right, and that locked in. So covalent bonds, how do they form? They form between by sharing pairs of electrons in the outermost shell or valence shell. So you have to have an unfulfilled valence shell, and they share this. Now, what I want to help you guys understand how this forms the molecules is there's a single, double, and a triple. So as we do a single, double, and triple, let me kind of show an example. Let's try CH4. Okay. So what we might see is something like this. Carbon forming 4 individual bonds here with hydrogens. Okay. So carbon, as we might remember, has a structure somewhat like this. Okay. 2 in the first, 4 in the second. Okay. Now, what I want to show you is if I have hydrogen with its one and only one electron that it has, in the first shell, then what we're going to do is be able to form a covalent bond. Now, remember, we're sharing pairs of electrons. Now, when I do this, I'll help you guys understand it. Okay, and my goal is to help you understand it. So let me help you understand this. Now, the deal is that each of these bonds here, you're sharing a pair of electrons. This hydrogen has one shell. That's the first shell. Its valence shell needs 2 electrons. It's only got 1 electron in it. It needs 1 more. So if it shares this and this, that means it gets both these electrons. But so does carbon because it shares the pair too. So carbon is going to get those. And the same here. So what carbon is getting is 2, 4, 6, 8 electrons. Hydrogen's getting 2, hydrogen's getting 2, hydrogen's getting 2, hydrogen's getting 2. And these bonds are referred to as a single covalent bond. And that is sharing 1 pair of electrons or 2 total electrons. Now let's say I want to make carbon dioxide, which is going to look a little like this. Um, Carbon double bonded to two oxygens. This is representing a double bond. Basically, this dash is representing that, okay? Now, what I want to show you here, let's again draw carbon. And carbon here with its first and second shell. Now, oxygen number 8 here, we got to put it over here. Let's start over here. We'll start right here. Okay, let's say we got an oxygen atom. All right. Oops, I was supposed to do there and there. Sorry about that. And then one more here. All right, let's do one there, two here, two here, one there. And then let's do another oxygen over here where we do the, I keep messing up because I see that and I think it's the nucleus. That's just the O and it messed me up and I apologize for that. Now, we're going to do that and then we'll come in here and draw the second shell, first shell, second shell, first shell, second shell. And what we're going to do is we'll do that. Let's do the opposite over here, okay? And what we're going to do with those is let's form a covalent bond. Now, we can form covalent bond here, and we can form a covalent bond here. And this is what is called a double covalent bond, a double covalent bond. And the same thing here. Just flipped around a little bit right here, okay? And that's, again, a double covalent bond. Now, let's say I wanted to make the molecule C2H2. Now, if you have two carbons here, 1, 2, 3, okay, you would have to do this. So we're going to do carbon-to-carbon triple bond. So what we're going to do, we're going to draw a carbon atom here. There's its nucleus. There's the first shell. Let's do 2 electrons in that first shell. Let's draw its second shell here, and let's do its 4 electrons. Okay. Now, carbon again. All right. And then hydrogen. So we've drawn a couple little hydrocarbons today is what they're actually called. So making sure I heard a weird noise. This is making sure my computer was actually plugged in. Okay. So I already got 1 and 2 there. Never mind. Okay. So here you're just going to get a single bond. Okay, you're just going to get a single bond. But here we're going to get 1, 2, and 3 bonds called a triple. Oh, baby, a triple. Sorry, it's triple. Sorry about that. A triple covalent bond. Okay. Now, that's how we form them, and I always like to draw them out and explain to you guys kind of what's going on, a single, double, and triple. Now, our goal here is to help you guys understand that's what's happening, okay? So, single bond, you are sharing 1 pair of electrons. That will be actually a total of 2 electrons. A double bond, that will be sharing 2 pairs. That's a total of 4 electrons. And a triple bond, that is sharing 3 pairs. That's a total of 6 electrons. Okay. Now, that makes them stronger as we go single, double, triple. And here we can see some examples of it right here. You can actually see a sharing a pair of electrons here, sharing 2 pairs of electrons here, sharing a pair here, sharing a pair there, sharing pairs here. We made methane. We made CO2. So methane was one of the molecules we made. We didn't make CO2. I mean, we made CO2. They don't have it here, but that's one that we made. Always like to show the singles, doubles, and triple covalent bonds that I can show it. And then here we have some different models to try to understand it. Now, um, one of the big things I need to talk about, though, is this idea of electronegativity. Now, this is new in the notes right here. I added this. You do not have it. I have it. I pulled it up. I like using it, and I wanted to make sure I showed it. So what we're doing is we're going to talk about the idea of electronegativity. Now, some atoms out there are very greedy for electrons. They have an unnatural, well, it is natural, but they have this very strong affinity. They attract electrons to themselves more. Now, right here, this is actually the higher up the element is, the more raised it is, the more electronegative it is. And what you guys will notice is things like fluorine, oxygen, nitrogen, things like that are pretty highly electronegative. Now, the least electronegative atom is this guy right here, francium. And francium is the least electronegative, and it goes up this way towards fluorine as the most electronegative atom on the periodic table, and it goes in this increasing up that way, generally speaking. Now, that is a nice way of seeing it, so you get an idea of electronegativity. Now, atoms who have a high electronegativity, we call them electronegative. They have a high affinity for electrons, and if they are electronegative, they tend to pull electrons towards them, so they don't share electrons equally. Now, we'll see if you share electrons equally, you're going to result in what we call a nonpolar covalent bond. These are atoms who are roughly the same in their electronegativity, so they make nonpolar compounds. These compounds are referred to being lipid-soluble compounds. Now, if you're dealing with a polar covalent bond, these are going to unequally share electron pairs, unequally share. So they're not going to share electrons equally. You have to have a more electronegative atom being in a covalent bond with something that is not as electronegative, quite low in electronegativity, and this results in an unequal sharing of electrons, forming what's called a polar compound that is water soluble. Okay? Now, one of the big things I always like to talk about when I do this is their solubility, because this basically like dissolves like. Things that are nonpolar molecules dissolve in nonpolar stuff, and things that are polar molecules dissolve in polar stuff. Now, in reality, I should use the word compound, because in a polar covalent bond, they will be compounds because they're going to have different electronegativities, and the same atom, if you're a molecule, just a molecule only, can't have different electronegativities. All right, now let's talk polar covalent bonds. Now, polar covalent bonds, you have an electronegative atom. Look at oxygen. Notice that oxygen is quite electronegative in comparison to hydrogen, who's not as electronegative. It's about one higher in electronegativity, roughly about one higher. But there is a tug of war that happens where the electrons from the hydrogens get pulled this way, and you can see it right here in a very good way. All of the electrons are getting pulled this way. So there's these two pairs here, or there's this pair here, and this pair here. There are two pairs sticking out the back, and there's none here. And you can see this fantastically in this diagram right here. So it's great to use that diagram. Now, the hydrogen atoms are very positive, partially positive. And the oxygen in is quite negative. It's partially negative. So you have a negative in, you have a positive in. We would say there's opposite poles, and they are polar. Water, for example, water and big white bears are both polar. Okay? Now, as we get that and discuss it, let's turn our attentions to ionic bonds. Ionic bonds, okay? The ionic bond is a very strong bond. When they're solid, they're strong, but they're weak when wet. So they're conditionally strong. Now, I always like to say it's bond, ionic bond, taken, not shared. We are going to steal an electron away from some other atom. Now, let's go over this. Let's talk about it. Let me help you understand this, and then we'll begin to look at some things. So let's talk about this in a way that I hope makes sense. Now, sodium atom, we might know, has 11 protons. And so let's take him and let's break it down a little bit. And then the third shell. Then there was the third shell. And we're going to put one right there. Okay. Now, this sodium atom, it has 11 protons, 11 electrons. So when we look at its charge, it will have no, no charge. Okay, no charge. Now, if we have chlorine, number 17, what we're going to see, guys, is something like this, okay? And I don't know if you can actually hear my dogs in the next room, so I apologize if you can. All right, and then one more shell. One more shell. Okay. Sorry if you can hear my dogs barking. Okay, so we've got this guy. Now, what we're going to see is chlorine has 17 protons, 17 electrons, and that also means the charge is also zero or neutral. 2, 4, 6, 8, 10, 12, 14, 16, 17. Okay, now if we look at that, they both have the same charge, and that's 0. What they are also is both are particularly reactive. But let's look at something here. Let's look at electronegativity. Electronegativity for chlorine is quite high. For sodium, it's quite low. So what is going to happen here is an unequal pull, and you have the opportunity for an electronegative atom and another fairly non-electronegative atom. And I need to add that to the notes here. That'd be something I'll do. Well, actually, I added it. I forgot that I added it here. I just haven't had that here. It's a less electronegative atom. I added it, and it's not in the notes you're looking at right now, but I wanted to go ahead and add that because if I don't sometimes do things that I'm thinking about doing, I forget. And it's things I just think that help. Now, let's take a look at this. Now, what's going to happen is this electronegative atom. This is some really kind of mean person. And we have a baby here, and we have candy. And this electronegative atom is going to steal candy from a baby. Okay, it's going to take this electron, steal this electron here, so it's no longer there. Okay, and the whole entire third shell is going to be gone. Okay, and sorry if you can hear my dog. So what's going to happen is we have 11 protons, but we only have 10 electrons. So in this case, there's now one more positive than there are negatives, so it will get a +1 charge, a +1 charge, okay? And so we're going to call it Na positive. Now this guy here, chlorine, it had 17 protons. That number doesn't change, but what's going to happen is it now has 18 electrons, so now has a -1 charge. So we're going to call it Cl minus, okay? Now, what is going to happen is we have these two different charges, and we call these ions. For example, this is now called a cation. This is now called an anion, okay? So, what we have, guys, cations and anions, okay? So what occurs is you have two atoms. One is more electronegative, and it will receive an electron from an atom who is less electronegative. And this results in a charged thing called an ion. Now, ions can be molecules or atoms. If it's a positive ion, it's called a cation. Cations are the electron donors. They give away electrons and become more positive because they actually have now one more proton than electrons. Anions, they are going to become what is called an anion. They get negative. Why? Because they accepted an electron, they become more negative because they now have one more negative, one more electron than they have protons. And this is going to create, guys, what we refer to as an ionic bond, where you have two oppositely charged ions and the strong association between them. But they're strong when solid and they're weak when wet. They're going to be like the Wicked Witch of the West. When you put water on them, they melt and they come apart. We'll talk about that more so in the water chapter, which is our next chapter. We'll talk about ionization. We'll talk about how things ionize. Now, what I want to help you guys understand is this is what we drew out here, okay? And just want to help you understand this is what's happening, okay? Now, this forms what we call salts or ionic compounds, like sodium chloride, calcium chloride, potassium chloride, some kind of salt. And what happens to a salt is this. When a salt, let's say I have NaCl, a salt, and I add it to water, what is going to happen is it disassociates, or we say ionizes. Disassociates or ionizes. Okay, it ionizes or disassociates into its constituent cation and anion in solution. This is why it's strong when solid, weak when wet. Okay? So I hope that made sense. Now, hydrogen bonds, on the other hand, we're going to talk about them now. A hydrogen bond, a little bit different. This is going to be with a polar compound who has hydrogen in it. Now, this is really a common thing to happen with molecules that have one electronegative atom bonded to hydrogen, kind of like nitrogen or oxygen. Those are two really good candidates for that. And then the van der Waals interactions are different parts of molecules, and we'll talk about those. Now, let's talk about a hydrogen bond. Now, as we look at a water molecule, I don't know why I drew this so small. And I don't know why I drew it so small. I was probably expecting to have more that I was going to draw or something. I don't know. Okay. Now, what's going to happen is there is a partially negative charge and a partially positive charge where the hydrogens are. Hydrogen has a partial positive charge. Oxygen has a partially negative charge. Oh, partially negative. I was getting ready to write. Now, what's going to happen is there will be that negative to positive interactions. The negative to positive interactions, and these are called hydrogen bonds. Hydrogen bonds. So hydrogen bonds form between molecules that are polar. You have to be polar and you have to have hydrogen in you. Okay? It's called a hydrogen bond. Now, hydrogen bonds are always between the partial positives and partial negatives of molecules that have, there will be a positive end and a negative end. This means it has poles, opposite poles. And these opposite poles attract positive to negative, like in this case, the ammonia to the water, and they attract and form a hydrogen bond. And these hydrogen bonds can help me form protein structures, help me hold DNA together, and also things like what makes your antibodies, for example, attach to the antigens on the surface of things that it's attacking. All right, now electrons. They also can accumulate in a molecule. For example, some molecules out there, what they do is they have hot spots of positive and negative. And these positive and negative hot spots can either act to attract or repel. Opposite charges will attract and like charges will repel each other, and they will end up in a position what we call that we refer to as a van der Waals interaction. Okay, and this is why you can have geckos walking up glass because they can actually form van der Waals interactions with their toe pads here. These little toe pads allow them to form van der Waals interactions with the glass. So temporary, little weak molecular interactions. Now, in living systems, and this is important, living systems, not all bonds, just living systems. The triple is strongest. Triple is stronger than double. Double is stronger than single. Single is still stronger than a ionic bond because ionic bonds in living systems are weak in water, and most living systems are roughly 2/3 water. And so ionic bonds are in the middle. Hydrogen bonds are always weak, and van der Waals, they're even usually weaker. So in living things, this is the organization. Now, this is a question they're likely to ask you guys on something like I'm trying to MCAT or something like that, the medical school examination, the MCATs. All right. Now, something I do want to mention, I always talk about is form fits function. When it even comes to molecules, it determines the functions. Here we have an example with an endorphin, which is a molecule, an endogenous opioid produced. Things like endorphin, enkephalin, endomorphin, dynorphin. These molecules, and sorry if you can hear my dog, these molecules will interact with the proteins. Now, the part of it that interacts with the protein, it is got a special structure. But morphine has the same identical structure on it. And it's that chemical structure that lets it bind to the endorphin receptors and block pain. Our natural painkillers, our natural endorphins, our endogenous opioids. Okay. If you can't tell, one of the reasons why it took me a little bit longer, I lost my voice yesterday. I'm just kind of getting it back a little bit today. I'm teaching heavy overload, so it's definitely kind of getting to my voice. So anyway, I'm sorry that I'm not as forceful and big right now. So, all right. Now, let's talk about chemical reactions. And basically what I want to do real quick is just basically mention that, okay, let's say I have A plus B yields AB. Well, we might call these things here the reactants. And we call this over here the products or the product. Now, same thing. If I have AB yields A plus B, we have a reactant. We have products. Okay. And this is what we call chemical reaction. Chemical reactions begin with reactants going into a chemical reaction and products coming out. I always like to describe it's kind of like it's like a play in football. A chemical reaction is making and breaking chemical bonds. Well, in football, you're making and breaking plays. When you make a play, you might end up putting something together and end up creating something like a first down, touchdown, or something. Okay. Maybe you intercept. Maybe you end up getting you end up breaking it. Maybe you get intercepted. You get sacked. You fumble the ball. Something happens. Okay. There's all kinds of things that can happen in a football play, just like in chemical reactions, things are made and broken. Plays are made and broken in football. The reactants go in. The products come out. Reactants get rearranged. Products are what you get rearranged into. Now, something I want to spend a little time talking about. And here we have an example of one. I'm going to use a different one, and I'm going to write it down on this paper so I don't waste too much paper. Is I'm just going to kind of come down here and write it, and I'm going to talk about this. It's something I would like to kind of talk about very briefly. It's not something I think needs to be talked about in a huge way, but it's something I'm going to mention here anyway. Is let's say I had carbon dioxide and I react that with water in the body. Okay. This is going to form a reaction here that is in balance, that is being the products are being produced, but they're also being converted back to reactants. It's going both directions simultaneously. And we can produce carbonic acid. Now, one of the things about carbonic acid is in solution, it will disassociate or ionize into this as well as this. Now, this is an equilibrium, and an equilibrium is pretty stable. Kind of think of an equilibrium as like this. It is like you are in balance. Now, sorry. This balance can be undone. Okay? And when it does, it shifts. Case in point. If I were to make loads of extra CO2, I'm going to shift the reaction that way. Okay? Sorry, I got a little bit messy there in my pen. I think when I moved, my chair shifted and it made me hit my elbow. So, all right. And this really should be the last thing we talk about. So, it goes to a chemical equilibrium. Okay, in a chemical equilibrium, chemical reaction, products and reactants are equal and it stays. But if you increase or decrease something on one side, it shifts the equation the other way, okay, to try to balance it out. So it makes it unstable, so to speak, okay. All right, guys, that is it. Thank you so much. Sorry that it took me a little bit longer. My voice was just not going to cooperate with me. So thank you guys. Have a great day. I'll see you in the next one. Maybe I'll go ahead and try to get it done this weekend as well. Guys, thank you. Have a great day, and I'll see you in lab on Friday. Thank you.